record. We want to find minimum cost path through a graph, right? So we constructed our graph, we sampled, we took collision-free nodes, and then we said, hey, we're going to connect these nodes with these edges. We're going to use the steering function to connect them. And then we're going to have a graph. We're going to have an explicit graph. Once we have the explicit graph, we're going to run A star search. A star search is going to give us a collision-free path through the space. And that is going to connect us between configurations, and that's going to be our motion plan, right? And so we talked about best first search more generally in Dijkstra's, and we started with this idea of best first search, where you weird where you start from like you have an open list and a closed list. Your open list starts with just the start, and you pop nodes from your open list according to some function f. You pop them. You check for every successor, is the cost through that node lower than the existing cost? And if so, you replace that cost and then add its children to the open list, right? And so that's the general idea of best first search. And then we instantiated it to form Dijkstra's algorithm by saying that the f that you're going to use to open things from that list is going to be equal to the cost. So f is going to be equal to g, right? And that gives you Dijkstra's or uniform cost search. And so that is going to have lots of expansions because it expands uniformly in all directions. Right? So it tries to choose the minimum cost thing. And so it's going to expand uniformly in all directions till it finds the goal. And we said, okay, that's great, but we're not using any information about the domain, right? And so we went from there to this idea of A star search. And A star search is the same as Dijkstra's, but that f is not equal to g. F is equal to g plus h, right? So the difference between A star search and Dijkstra's is this f function, right? So f is equal to g plus h. Everything remains the same. And we went through this example and we saw that you saved one expansion, right? And as you go to bigger and bigger and bigger problems, you save more and more and more expansion. And so the key idea of A star search is that you're leveraging this heuristic. The heuristic is domain knowledge. It tells you which things are promising, which things are not. And that kind of directs your search, right? That directs your search to not expand things that are irrelevant. So we talked about heuristics being admissible and consistent. Admissibility is a condition about being an underestimate, and consistency is a condition about monotonicity along a path. And if your heuristic is consistent and admissible, then you can show that A star is optimal and is sufficient. But we said that, hey, this is not always the right thing to do because your memory may grow exponentially. And so you often do this thing called weighted A star search, which is a little suboptimal, but it often saves a lot on memory and compute, right? And so weighted A star search is just taking your heuristic and weighting it by some function epsilon, which is greater than 1. And so it's saying that you're trading off some of the optimality for the sake of expanding listeners. And so the whole idea of weighted A star is just trading off optimality and computational efficiency. Alrighty, so that's what we covered last time, right? And so from there, we're going to go to the idea of lazy search. And so lazy search is asking a really simple question. It's saying that, okay, we're doing the search process. We've talked about node expansion and these kinds of things, but let's really look at, where is the most expensive step of a search procedure, right? And so if you look at like most problems, the thing that makes search really expensive is edge evaluation. If you have two things, you're trying to evaluate, is there a collision-free path between them, right? That is often the most expensive thing. So like, for instance, for non-convex shapes, if you're trying to evaluate if there's a collision-free path between them, you have to run your expensive collision checker a bunch of times. And so in most problems, many problems, edge evaluations are the most expensive bit. So this is a graph from this paper. It's even hard to see how it's like edge evaluations versus other. You can see the whole graph is basically dominated by edge evaluations for some of their problems. And so what lazy search is trying to do is it's trying to minimize the number of edge evaluations. And so what that means is it's going to reorder the way that you open nodes so that you try to evaluate edges the least frequently. And when I say evaluate edges, I mean, given Q1 and Q2, 2 points in configuration space, you want to check whether it's collision free or not. Okay? And so the idea of lazy search is just to like procrastinate as much as you can. So you reduce the number of edge evaluations you have. And so if you think about best first search, right? So best first search is going to start at some state S. It's going to open state S. And then it's going to check its neighbors SA, SB, and SC to see if they're in collision. And if they're not in collision, then it checks is, G of S prime less than G of S plus C SS prime. It checks that condition. It checks if it's in collision. And if it is, then it adds it to the queue, right? And so when I expand S, I'm going to collision check, collision check, collision check. So I'm going to evaluate all three edges, right? And so I've done this as soon as I expand F, I've done this relatively expensive process of checking this, and checking this. But the question we want to ask here is, let's say the optimal path was to go through B and C was just like a bad path to go through, then I like unnecessarily wasted a check on C when I really didn't need to. And so the idea of lazy search is how do we reorganize when we do those edge checks so that we avoid checking S to C, right? So you save on that cost. And so maybe this is like the opposite of life lessons, but the key of lazy search is procrastinate as long as possible. Not what you should do for homework for, but it is what you should do for lazy search. Procrastinate as long as possible until you know that something is like a promising candidate. And so don't waste your edge evaluations on things that may not be promising. And so it's just reordering when you evaluate. And so we're going to talk about lazy A star. But there's a bunch of different lazy search algorithms. Your reading has a lazy search algorithm, lazy SP, and that should cover more. But the idea behind lazy A star, lazy weighted A star, is when you're expanding a node, don't collision check the successors when you're adding a node. When you're expanding, let's say S, don't collision check SA, SP, and SC. Right, so you should just be optimistic and assume that everything is a valid edge. But instead, when you expand a node, you collision check it with its parents, right? So it's like I would never like in the previous example, essentially what it's suggesting is when you're expanding S, don't collision check this, this, and this. Instead, add this, and add this without collision checking, and only collision check the node that you expand next, right? So it's like when let's say I added A, B, and C to my like queue, right? What'll happen then is that I assume that all of them are collision free. And let's say the next most promising thing to expand was B. Then I only check the collision of B with its parent, right? But what I did is I avoided having to check SA and SC, and I only checked the promising one. Right? And so all that lazy search does is it moves when you do the edge evaluation. So you only check the most promising things, right? So don't collision check an edge when you're expanding the parent, or collision check an edge when you're expanding the child. That's it. So we'll go through some examples, but that's the high level logic here. If you're doing this, you can have multiple copies of a node in your open list, as opposed to another A star you wouldn't. But you would have to like check all of those. So non-lazy A star looks something like this, right? So non-lazy A star says, you're going to like pop the thing with the smallest f. You're going to like insert S into closed for every successor of S. Let's call it S prime. You're going to check if SS prime is in collision. If it's in collision, set the cost to infinity. And then you're going to check this like GS prime condition, right? That's what A star search normally looks like, is that you do this like edge check when you expand S, you check all of its children, right? So you like say expand S, check SA, SB, SC. What lazy A star is going to do is it's just going to shift things around. So it's going to like, in this part of the code, it's not actually going to check if something's in collision. It's going to assume that it's not. But when you're going to open something by popping it from F, then you're going to check if it's in collision, right? And so you're not going to check the children. You're not going to, when you expand a parent, you're not going to collision check all the children. Instead, when you expand something, you're going to check whether it collides with its parent or not, right? So you're going to store all the nodes in the list along with their parents. When you pop a node, you collision check, is it in collision with its parent? So let's go through an example, and this will become a little more clear. So let's think about this setting, right? You have this like starting state S, you have n edges, which are all in collision, right? So like these are like different, these guys, Jesus. These guys are like edges in collision, right? And then you're going to have like the optimal path to the goal is S, B, A, G. Uh, let's consider that to be the optimal path. That doesn't actually look right, right? It should be SAG. Okay, but we renamed this. It doesn't matter to make the point. There's a mistake on my part. Um, but if I did A star search, right? Let's say I started from S, what would happen is that I like add each of its children. Like I say, I expanded S. I looked at every child of S, which is going to be n children plus A plus B. And when I expanded S, I did n plus 2 collision checks. And that is like way too many collision checks because we kind of know that the heuristic will tell us that these guys are not actually that promising. And so instead, if I could only collision check this guy and this guy, then I'm like much happier. And so what lazy A star will do is it like when you expand S, you don't collision check all of these guys, right? You just like add all of these guys into your queue, right? And then you only, when you expand B or you expand A, only then do you collision check its path with its parent. Um, oh, you know why this example makes sense is because S and A is in collision. Yeah. I didn't make a mistake, but it's because S and A is in collision. So S and A is in collision, S and B is not in collision. So this is in collision, this is not in collision, and so the shortest collision-free path is SPAG. Yeah. You usually set the cost to infinity. So like that, you'll never consider that path because the cost is um you often, yeah, I guess you can either collision check when you build the graph, or if you're incrementally like building, if you get the nodes first and then you're incrementally checking the successors, then you can collision check while doing search.
So you would just connect all the edges that are within a certain.
Exactly. Yeah. Right. Good question. Um, okay, so what lazy A star would do is it'll start from S and it'll put in B, A, X, all of these guys into the queue, right? Basically assuming that they're not in collision, not doing a collision check. And then it picks the next most promising thing, right? Which, so like previously we had B, A, and X, right? So it opens the next most promising node, which in this case is B, right? So it's going to open B, and then it's going to put like A into the queue. But remember that there's two copies of A now, A from S and A from B. Like you could either go this way or you could go this way, right? So if you look at the like queue earlier, the queue earlier was there's B, there's A, and then there's all of these X's. The most promising one is this B. So you expanded B. Its only child was A. So you're going to add A into the queue. But you're going to label that A. This is the A that came from B, not the A that came from S. And those are two different A's. So one of them is going SBA, one of them is going S to A. And so you're going to label these two as different ones. Now, now what's going to happen is you choose the best one, right? So the best one is going to be A from S. That's the most promising one. You check it, and then you say, hey, this is actually in collision. And so I can't support that. So I skip it. And then the only thing left is, or there's also all of these other ones, like X is still in the queue, but the most promising one is at that point is A from B. You check it, it's collision free, and you're kind of done, right? But what you did in that process is that you like avoided expanding all of these guys, right? And so in this process, you get to SBAG without having to expand all of the other nodes in the process. So all that lazy search did is it like didn't collision check all the children while expanding the graph. It instead collision checked only, you put it in you put it in the queue, assuming that it's not in collision. And then you only collision check when something is promising and it's actually popped from the queue, right? And so all that lazy star does is it just reorders things out. Make sense? Questions? Okay. So that's all the lazy A star is. Lazy A star is what you'll implement in your homework. But just remember, you only like just this pseudocode is what you want to think about. Like you only open things if it's like promising. You only collision check if it's promising, not if it's just expanding from its parent, right? Alrighty. So that's the first idea we're going to talk about today, which is lazy A star. Any questions about A star before we move on? Alrighty. So the next idea we're going to think about is this idea called RRT, which I think is awesome. But RRT is an idea from the 90s, but I think it's great. So the things we've discussed so far are what you call probabilistic roadmaps. And probabilistic roadmaps basically mean you generate a bunch of nodes through sampling. And then you like try to construct a graph and then you try to search that graph, right? And so you're like, hey, like sampling all over the place wastes a number of points in parts of the space that are not actually needed. And it requires solving this like 2-point boundary value problem, right? Like when you have a system like your car, you can't just connect anything to anything. You have to solve this boundary value problem. And so these PRMs, which are basically like construct a graph through sampling and then connect nodes, are a little wasteful, right? And they like are overkill in many cases. You just care about going from the start to the goal. You don't care about building a graph to go from anywhere to anywhere in many cases. And so the idea behind RRT and RRT star is like, can you build up a graph or a tree incrementally? So it's called the Rapidly Exploring Random Tree, RRT. But it's basically like, instead of trying to build the graph at once and then searching it, it's like, can we build up a tree incrementally that gets you to the goal? Right? And so in doing so, what it helps you avoid is it helps you avoid like wasting a bunch of samples on things that are unnecessary, and it avoids having to perfectly solve this 2-point boundary value problem. And so RRT is somehow still one of the most popular motion planning algorithms, though it's like 20 years old. But it's very, very simple, right? So the idea is from 98. Most of you weren't born then. But RRT was still going strong. And the idea of RRT is that A star, it explicitly constructs the whole graph to store in memory. What RRT tries to do is sample a tree on the fly. And so you're like, rather than construct, as I said this at the start, but you're instead of trying to construct an explicit graph, you're trying to construct an implicit graph. And so like you don't actually store the whole graph in memory, you only grow it as you go. And as a result, you don't waste as much time on memory. You can avoid this 2-point boundary value problem. I'll talk about how. But it tends to be a lot more practical for many problems. Right. So the basic idea of RRT is that you sample next points randomly in the configuration space, but rather than building like an explicit graph of rather than saying, hey, I'm gonna take this whole thing, sample, construct the whole graph. It's like, this is my start. I'm going to like sample one thing, connect it. Then I'm going to sample another thing, connect it. I'm going to sample another thing, connect it. I'm going to sample another thing, connect it. And so like, it's more like incrementally building a tree from the start to the goal, rather than trying to build a whole graph at once, right? So it's like an incremental algorithm. And so you can still do like tree search, still do search. But generally search in a tree is easier than search in a graph. And so it's more efficient. But it's not always exact. It's like a sampling-based algorithm, and you'll see that some of the solutions are like kind of wonky. They're like kind of roundabout. And so let's go through the algorithm and we'll try to intuit what's happening. So this is the whole algorithm for RRT. RRT says that like you are going to like start by just having a tree which only has the initial state in it, right? And then what you're going to do is you're going to sample a random state from the configuration space. So like, let's say this is your configuration space. This is what you call X init. Okay. You're going to say, I'm going to sample a random point. And that's going to be your X rand. Okay. And then let's say you had some tree built up so far. What you're going to do is you're going to find the nearest neighbor in your tree to that point X rand. So this is called, let's say this is X rand. You're going to find your nearest neighbor, which is going to be X near. right? So you start with a tree with only the initial node. You're going to sample a random state. You're going to find the nearest neighbor in the tree thus far. Okay. And then what you're going to do is you're going to try and this step 5, the select input step, it's going to try and find a control that gets you from as close as possible from X near to X rand. Right? So X near is a thing that's already in your tree. X rand is a point that you like randomly sampled in the space. And then this select input is trying to find a control that takes you from X near to X rand as close as possible. But the reason it's important is because you don't have to exactly solve it. Like U doesn't need to be an exact solution to the problem. It's just our best possible guess. Um, and then once you've done that, then you just like propagate forward through the system to get a new state. Let's say like the U didn't get us exactly to X strand, it got us somewhere nearby. And so we're going to add this new state, X new, into the tree, and we're just going to repeat, right? So it's like you choose a random state, you find the nearest neighbor, you try to find the best possible connection between the nearest neighbor and that random state. You play that best control forward to get a new state. You add that new state to the tree, and then you repeat, right? And so you're never actually solving the boundary value problem between these two things perfectly. You're just saying like do your best, and then like get from here to like wherever you can get, which is best, and that becomes the new point you add in your tree, and you keep repeating, right? And so you'll say, okay, I added this thing, and then this X strand is irrelevant at that point. So I've added this new state. Now I'm going to sample, let's say, another point. And this other point will have this thing as the nearest neighbor. I'm again going to try and get from here to here. That'll bring me to here. And then this point is irrelevant. And so you like keep expanding your tree this way, right? But as a result, you're never storing the whole graph in memory. You're only incrementally building up. And as soon as you reach something that's close to the goal, you're done. Right? So the idea of RRT is incremental search, says in you're like incrementally increasing this tree from the start till you get to the goal, and then you're done. Yeah.
So this thing like randomly anyway.
Uh-huh.
If you have, let's say you have a hard point like this, why don't we send?
Yeah, so people often do heuristics like that. They like control how RRT sample. But the initial version of the algorithm, the reason it actually samples randomly is because it like randomly sampling biases you towards the like biggest open space. Whereas like this kind of thing might get stuck in certain corners. Like like we'll show in the next slide, it like randomly sampling biases you towards the biggest space, and that like tries to fill out the space as quickly as possible. So the next question is how to sample, right? And so if you just executed controls randomly from the start, it would lead to something that looks like this, like because like Brownian motion, you just like Brownian motion around, it kind of leads to this. Whereas if you look at RRT, it often looks something like this. So it's like much more, looks like kind of weird bacteria growth, but it's like it like gives you much more spread out sampling. And we'll think about why, but it really comes from the fact that you're first sampling something randomly from the configuration space and then finding the nearest neighbor and trying your best to expand towards it. And so the idea here is that when you are selecting a random point, it's biased towards the largest Voronoi region. So have you guys heard of Voronoi cells? No? So a Voronoi cell looks something like this. A Voronoi cell is like, let's say you had like some set of points, right? A Voronoi cell is the set, like a Voronoi cell for this point is the set of points that are closer to this point than to any other point, right? And so you can kind of divide up. These also look like biological cells, but you can kind of divide up any space with a set of seed points into these Voronoi cells. And Voronoi cells say that like all of these points, if I measure their distance to any other point, like they're closest to this point than they are to this point or this point or this point or this point or this point, right? And so you can kind of think of them as like kind of clusters, right? And so what random sampling does is it biases your expansion towards the largest Voronoi region when you do RRT. And the logic is just that the largest Voronoi region covers the most space. And so like it has the highest likelihood of being sampled, right? And so like as a result, so I think it'll be different if you just like imagine that you took a point on the tree and just randomly ran control. That's not what you're doing. You're instead sampling a point randomly in configuration space and expanding towards it. That is a little different than taking a point on the tree and just like doing random controls. So like random controls is different than random states. And so RRT is nice because it like solves the exploration problem a bit. It like expands towards the largest Voronoi region. That's why it looks so spaced out. Okay, so if you look at what RRT trees often look like, they look something like this, right? And then if you want to like, once you've expanded these things, the things over here are the Voronoi regions, things on the bottom. And you can see that like it kind of covers the largest Voronoi regions, and the largest Voronoi regions become smaller and smaller and smaller and smaller. So it densifies the space. But let's say you started from here, you wanted to get to here, like you then search the tree and you're like, this is my path to the goal, right? And so the difference between that and A star search is that A star search would first construct all of this stuff, but it's not incremental. It like will construct the whole graph and then search it, right? So let's see, do we have some nice graphics here? So RT growth looks something like this. Like you can see that it like densifies the space. So often at the start, it's going to take like big steps in the space. And then you start to like fill in the space more and more and more and more and more. And so RT is one of these like asymptotically complete algorithms, which means that like the longer you run it, the higher it has a chance of finding a collision-free path to the goal. So it's like probabilistically complete. So it's not always going to find a path to the goal, but with high likelihood in the limit of infinite samples, it'll find a path. Okay, so that's RRT, right? Some practicalities here are that when you, so there's a few different functions in RRT, right? So there's choosing a random state, that's just like randomly sampling. You do uniform sampling. But then there's the question of like nearest neighbors. So you have to find the nearest neighbor. So often you'll store your states in a KD tree. KD tree is a data structure to do the nearest neighbors very efficiently. Or you do an algorithm called locality sensitive hashing. It's again to find nearest neighbors very quickly. And then you have this like select input function, which says that you sampled a random state, you took the nearest neighbor, you want to do as well as possible to go from the nearest neighbor to the rand. But you, unlike A star, where you have to solve the like edges exactly, here what you do, you just do your best, right? So you just say, let's try to approximate our boundary value problem. And so some people will solve it approximately, some people will just try random things and choose the best one, right? So it's like, it doesn't need you to solve how to get from here to here exactly. It just says, try to do your best to get from here to here. You get here, now add this thing to your tree and continue, right? And so the nice thing is that you can be approximate in how you solve this problem, right? And so like, if there's no obstacles and you can just teleport through space, then you can obviously like connect magically from here to here. But if there's obstacles or if it's non-holonomic, right, then you might not be able to reach it exactly. Like for instance, you're trying to get from here to here, there's an obstacle here, you like stop it right over here. Or if you're trying to get from here to here and your best paths are like this, you like choose the best one, right? And so you're reducing the burden of perfect solving on the algorithm. And so that's what makes it nice. Now there's like other extensions we can do. So one of the algorithms you'll cover in your reading group is RT Connect, which is similar to bidirectional RRT. But RRT expands from the start to the goal. What bidirectional RRT does is it says, let's go both ways, right? Like, let's go from the start to the goal and let's go from the goal to the start. So it's like two trees. And then you try to meet each other, right? So like what bidirectional RRT does, it tries to expand a tree this way, tries to expand a tree this way, and then every so often it tries to connect the trees. And so the idea behind bidirectional RRT is that like to get from here to here, you have to like cover this volume, and that is a bigger volume than if you started in both directions, because this thing is not informed by the goal. Right? Whereas you start from both directions, it's informed by the goal. What might be a problem with the bidirectional RRT? Like, are there situations where it might not work?
I'm looking like what if it's like a very old code that it's trying to connect with.
Yes. Yes. Yeah. So you might have pretty suboptimal solutions if you're like trying to connect to like this guy to this guy or something. That might be bad. So you probably want to connect this guy to like this guy. Yeah. The other thing is if your system's not reversible, that could be tricky, right? a system's not reversible, you can't just go backwards willy-nilly. So there's ways to solve that still, but that's sometimes true. And so you can go, this becomes more and more of a problem as this, imagine this sphere in like n-dimensional space. This becomes more and more and more of a big deal in n-dimensional space. But you can kind of go from there to multi-start RRT rather than bidirectional RRT, you can do multi-directional RRT. So here's an example, which is kind of like, we have these narrow passages, right? Sometimes starting from one side, the chance of getting through a narrow passage randomly is really small. But if you start from the other side, getting through the narrow passage is easy, right? And so what often happens in these examples, if you can start from multiple directions, then you can get through narrow passages more easily, which is really the hard problem in most motion planning. It's like you're trying to traverse like a tunnel, and it's like hard to get things through the tunnel. Okay, so that is RRT. Any questions? Okay. So why is RRT potentially not what we want? Like let's look at some of the RRT paths. If you look at the RRT paths, like what's the issue with these paths? Like I want to get from there to here. Like, why is RRT not good enough?
Yes, they're maintenance to factor like so you're
Yeah.
really long to each with them.
Exactly. So they're not very efficient. And so RRT guarantees that you'll find a path. It's not guarantee that you'll find an optimal path, right? And so when you go from RRT to RRT star, the challenge we're trying to solve is an optimality challenge in the sense like, are we finding things that are close to a shortest path to get from the start to the goal, right? And so RRT in general leads to these very jagged roundabout paths. And so if you ever see an RRT algorithm and do this kind of shit, and like instead you want to go to an RRT star style algorithm, which will help you find much smoother paths. So maybe if I can jump to the result difference, RRT gives you things like this, and RRT star gives you things like this. Right, so it's like a very, very large difference. Like you look at the path is shown here in red, versus like, right? And so RRT star helps you go from here to here, find optimal paths. Okay, so let's invent RRT star. How do we get from RRT to RRT star? Like what's the trick? Like we've been expanding these trees, and these trees they don't seem that optimal. Is there a way for us to find more optimal paths? So let's go back to our algorithm. So like here, right, in our algorithm, we just sample something, we connect it to the nearest neighbor. But like the path may not have been like the most straightforward one to get there, right? Like, so for instance, I'm like trying to like grow my tree, like let's say I sample this guy. Like it could be that this one connected to here, but the path to get here might have actually been shorter this, right? And so if I wanted to change this algorithm to get the paths to be more direct, how do I do it? Approximately, we don't have to invent the exact solution. Give me the vibes. Yeah, so it's kind of like that. Basically, you do this thing called rewiring. And so what rewiring does is it says, okay, you like sample this thing, and instead of just connecting it to its nearest neighbor, you're gonna like look in the neighborhood and say like, is there a better option for me? Right? Like I've decided I'm gonna add this thing. I'm just gonna like check to see if there's a better option. And so instead of now sampling this thing and connecting it to this guy, you're gonna sample this thing and then see is there a better option? If there's a better option, I'll connect it to this guy. Right? So like the paths, like you're factoring in cost while you're building the tree, whereas in RRT, you're not factoring in cost as you build the tree, right? So you build the tree and then you find the lowest cost solution. Whereas in RRT star, you're going to factor in cost while building the tree. And so the idea in RRT star is that as you like add a new point to the tree, you're going to like do two things. You're first going to try and see, okay, this is the nearest neighbor I chose, but is there a better path? Like once I did this thing, is there a better path to a different node, which will be shorter? And then the second thing you're going to check, second thing you're going to check is like, if I went through this node, can it give me shorter paths to other nodes? Right. So you're gonna check for a new point, let's say x new. You're gonna check, can x new be reached through shorter paths? And then you're gonna check for near neighbors, xn, does going through x new make the path shorter? So like both, like can xn make x new shorter and can x new make xn shorter? Right? And so the key idea in RRT star is that when you're expanding the tree, you check if like going through that node makes the path shorter in terms of cost, and then you like construct the tree accordingly. So the tree is much less wiggly and much more straight line. And so this is the like somewhat complicated looking pseudocode, but it's actually almost the same as RRT. So we're gonna walk through this like convoluted mess, but it's going to be very similar. So this is basically sampling a random node. This is finding the nearest neighbor. This is choosing the best possible action to get from X near to X rand, right? And it's going to say that this is the new state that I reached. This is my best effort state that I was the same as RT. So far, we're the same as RT. Now, here's where the difference comes. There are these two for loops. You don't have to parse them that exactly. But what it does is it says, if I have a new node, X new, it's in RT, it would just connect it to X nearest. It would just connect it to the nearest neighbor that it chose as its parent, right? What RT star is going to do is it's going to look in a nearby radius and say that, is there a better option for me? It's like hedging your bets. Is there a better option for me to get to X new? So it's saying like, imagine that let's try and draw an example. So let's say this was X near, this was X rand, and like, let's say your tree actually went like this, and let's say this was like X new. Okay. So normally what RRT would do is it would just connect this guy to, it would just connect this guy to this guy, right? So RRT would connect these two things, like this connection would happen. What RRT star is going to do is rather than just directly connect this guy to this guy, rather than directly connect X new to X near, it's going to look in a radius and say, hey, actually, maybe connecting to this guy will give me a shorter path, right? So it's going to say, let's call this like X neighbor or something, right? So it's going to say, hey, actually connecting to this guy from here is a better option than connecting from the original parent. And so I'm going to take that better option, right? And so it'll always go towards shorter paths. So if you can get a shorter path, it'll take the shorter path, right? And so when you're doing RT star, you're not just expanding to the nearest neighbor, you're trying to like see if there's something better, right? And so this whole for loop is saying, is there something better than the nearest neighbor that I first started with? And then the second for loop here, which again looks pretty complicated, is just saying that like, let's say I had my same tree, I like decided on this new point, let's call it X new. It's saying that for other nearby points, like maybe, let's say there was like, maybe there was like a part of the tree that looked like this. It's saying that for other nearby points in the radius, is it actually easier to reach those points through X new? So the first for loop says, can X new be reached more efficiently through neighbors? And the second for loop is saying, can neighbors be reached more efficiently through X new? Right? So it's saying, actually, I don't need to take this whole path of the tree. This thing can actually be reached more efficiently this way. Or I don't have to take this whole path. This thing can actually be reached more efficiently this way. And so this is what you call rewiring, right? So when you're like, it's basically saying, if whenever there's a more efficient path, take the more efficient path, right? And so that's what makes the lines much straighter. And you can prove that it's like close to optimal. And so that's all that RRT star is, right? So two parts. If you can find a better parent, find a better parent. If you can help children, right? And so that's basically all that RRT star does. Questions? Make sense? Okay, so if you look at what RRT star looks like around like the lines you see are like much straighter and look much less fractally. And so in practice, you'll often use RRT star algorithms. They don't like lead to as much jagged paths, especially if you're trying to combine with machine learning algorithms. Like RRT star algorithms are much better than RRT. And so you can see here that like the path looks much straighter than if you like did RRT, which was very like jagged in its path through the space. Alrighty. You also do often when you do motion planning, you often do this post-processing step. So once you've like found even RRT star still has some jagged parts, and so after you've done like planning, you often do this, post-processing step, which tries to make the paths as smooth as possible. And so before using a path, you often like post-process it. And so you do two things. First one is called shortcutting. And so if you like, let's say you had a path that goes like this, right? You do shortcutting, which says pick two vertices, right? And if you can connect them directly and get to a shorter path, do it, right? And so it's like this will make this path shorter. So then this thing goes with, right? And so that often makes your like paths way smoother and way more direct. And then the second thing you often do is like you want more constraints on your system, like you want it to obey certain smoothness properties, or you want it to obey certain velocity constraints. And so you like run it through an optimization process. So you'll initialize from your motion plan, and then you'll run it through an optimization process to be better. Okay. Last thing to cover here is Max Likachev is a big pioneer in this space at CMU. And so I just copied this from his slides, but his opinion generally is that for continuous spaces, sampling-based methods like RRT and RRT star are much easier to get to work, right? And so they like don't require careful discretization. You don't have to be very careful about the space. And it's like often much more compute efficient. And it often like doesn't need to solve this 2-point boundary value problem. And so he recommends in a continuous problem, try to use RRT or RRT star. And you also can avoid designing heuristics. In most cases, you can avoid designing heuristics. The trade-off is that A star often generates more optimal solutions because you're not like generating these jagged paths. And if you like know a lot about your problem, you can make A star very efficient. You can like use lots of GPU parallelization or like be compute efficient and give yourselves like really fast solutions, but it has to be kind of domain specific. And A star can be applied naturally to both discrete and continuous problems, whereas sampling-based RRT is like inherently a continuous space algorithm. And so generally he suggests that A star is a little hard to use for continuous problems, but RRT and RRT star are a lot easier to use, but they give you less optimal solutions. So it depends on the trade-off you're looking for, but in practice, RRT, RRT star, and related variants are used a lot more. All right, I think that's all we have for today. And we'll start with machine learning on Monday. Alrighty, thanks. Have a good weekend.